Imagine you lived in a world with only two shapes. Let's call them rubes and gears. You live your entire life knowing only these two shapes. Then one day, a friend tells you that she's discovered a new shape. It's sort of rube, but not exactly. Of course, it's sort of rube because it's a cube, but it's not red. Your language has not yet developed the words to distinguish between the object's greenness and cubeness. There is a very similar situation in the real world with the mathematical notion of compactness. For most of your math education, you've understood finiteness as one concept. It turns out it's actually two: discreteness and compactness. When trying to give intuition for the concept of compactness, it's often said that it's sort of like finiteness, but not exactly. This is because compactness captures just part of what it means to be finite, with discreteness capturing the rest. But most of us have never encountered the idea of compactness by itself before, completely isolated from discreteness. So we are just like our friend who never encountered cubes that were not red. It doesn't mean she can't understand it, just that it will take some clarifying of new terms and a little time to get used to a whole new outlook, which is what we will now do for compactness. Compactness is one of the most important concepts in modern mathematics. Central to topology and analysis, it can also be seen as a kind of gatekeeper topic. If an undergraduate math student does not understand compactness, whatever it really means to understand, it is unlikely that he or she will be able to do higher level math. To truly grasp the meaning of compactness in a deep way, as well as to appreciate the connection between finiteness and compactness, we'll now take a brief tour of the historical development of this concept. We'll see the various definitions of compactness that have been proposed, and the specific contexts in which they are equivalent. The first person to coin the term compactness was the French mathematician René Maurice Fréchet. He did this in a 1904 paper leading up to his PhD thesis just 2 years later, where he also defined metric spaces for the first time, which, if you haven't learned about, they are essentially spaces for which a mathematically precise notion of distance has been defined. In his thesis, Fréchet considered three kinds of spaces, which he called V-class, E-class, and L-class, where E is the least general space and L the most general. The E-class are metric spaces. And while Fréchet was hoping to define a notion of compactness for all three of these, he was unable to do so. Instead, he offered the following definition for metric spaces. Suppose you have a set E and take a closed, non-empty subset of E. Call it E1. Next, take a closed, non-empty subset of E1 and call it E2. Continue this process indefinitely, taking a closed, non-empty subset every time. What you have here is an infinite sequence of closed subsets of E. If there exists one element that is in all of the E_n's, then we call the set E compact. What this definition does is to rule out sets that run off to infinity. For example, the real line. We can see this as follows. Take the first subset 1 to infinity, then 2 to infinity, 3 to infinity, and so on. Each En is a closed, non-empty subset of the one prior to it. But there's no point that belongs to all of the subsets. The intersection of them is empty. So the real line is not compact. And any other sets which run off to infinity are not compact as well. If you're wondering how Fréchet came up with this definition, I'm afraid even he couldn't remember. Later in life, he said, "Doubtless, I wanted to avoid a solid dense core with a single thread going off to infinity being called compact. This is a hypothesis because I have completely forgotten the reasons for my choice." Nevertheless, here we begin to see how compactness is sort of like finiteness. We'll call this Fréchet compactness and move on to the next definition, which was due to the German mathematician Felix Hausdorff. It occurred in a book he published in 1914. For Hausdorff, a set E was compact if every infinite subset of E has a limit point in E. If we call the limit point X, then this means that if you consider a neighborhood around X, no matter how small, it will contain infinitely many points of the larger set E. So in some sense, infinite subsets are sort of capped off at the ends, a notion which is again similar to finiteness, but not entirely. A nice example to illustrate this type of compactness is the interval from 0 to 1, including the endpoints. If we consider the infinite subset of all points 1 over n, for which n is greater than or equal to 1, then its limit point is 0. So the entire set and its limit point are contained in the set we're calling E now. This works for all infinite subsets of the closed unit integral. So according to Hausdorff's definition, it's compact. However, if we remove one of the endpoints, it's no longer compact, since the limit point no longer belongs to E. Today, Hausdorff's definition of compactness goes by the name of limit point compactness, and for metric spaces, it is entirely equivalent to Fréchet's earlier notion. But in the context of more general spaces, they aren't the same. Before I explain further, I'd like to mention something personal for me that's related to what is the most important metric space for us all, planet Earth. It can feel overwhelming when we look at the enormous problems facing our planet today, from ocean waste to the destruction of biodiversity and the ever-increasing number of endangered species. The gap between the scale of the problem and what one person can actually do is exactly why I'm a member of Planet Wild. They're a community-based nature protection organization. It's essentially crowdfunding, but for nature. Every month, we as a community fund new missions that clean up oceans, rewild forests, and protect endangered species. And they document all this amazing work with a video every month published right here on YouTube, so I can directly see the impact of my contributions. One of their recent missions contributed to building one of the largest wildlife corridors in the world, connecting Yellowstone to Yukon, the largest intact mountain system left on Earth. The network they're building will help wildlife to roam safely for the first time in generations, saving animal and human lives, as well as billions of taxpayer dollars in the process. You can learn more about this in their amazing video, which I've linked below. The best part about Planet Wild is that they make it incredibly easy for anyone to join and become a part of their community. You can sign up for whatever amount feels right for you and cancel at any time. The first 100 people to sign up using my code ABIDE4 will get their first month paid for by me. Just scan this QR code or click on the link in the description. You'll immediately have an impact and see the result in less than 30 days. Hausdorff's definition of limit point compactness was the standard definition of compactness for the next 15 years. It would eventually be superseded by a more general definition due to the work of two Russian mathematicians, Pavel Alexandrov and Pavel Urysohn. In a paper published in 1929, they clarified the definitive notion of compactness. By this point, the subject of topology was experiencing significant development, and the notion of a topological space was firmly established. In essence, a topological space is the most general of all mathematical spaces. It consists of points where a very loose definition of closeness is defined. The technical way this is done is by taking a set and adding the structure of a topology on it. I made an entire video about what a topological space is and how it fits into the hierarchy of mathematical spaces. So if you're interested, go check it out after this. Now, Alexandrov and Urysohn's definition of compactness applies to topological spaces. And since they are the most general, it necessarily applies to all the spaces below it as well. The definition is incredibly simple. A topological space X is called compact if every open cover has a finite subcover. In order to fully appreciate this definition, we need to know a few more things about topological spaces. First, for any set of points S, we can consider three related sets: the interior, exterior, and boundary of S. The interior consists of all points which can be enclosed in a ball that is entirely contained in S. The exterior is all the points that could be enclosed in balls that are completely disjoint from S. And the boundary of S is all the points which are enclosed in balls that are partially inside or outside of S. Now, depending on the set, the boundary of S may or may not be part of S. If S contains all of its boundary, then we say that S is closed. And if it includes none of its boundary, then S is open. All these terms will then apply to any set or subsets that we have in our topological space. In fact, applying a topology to a set just means defining which subsets are open. And this concept of openness is pivotal for understanding compactness, which brings us to open covers. An open cover of a set S is just a collection, finite or infinite, of open sets that cover the entirety of S. And a subcover is a subcollection that still covers all of S. A compact space is therefore a space with the very special property that for any collection of open sets you take to cover it, you can always find a finite subcollection that will still cover the space. Again, we see that there is some connection to finiteness here. The connection becomes even more apparent if we consider the following statement that is true for finite sets, but false for infinite ones. All functions are bounded. For a finite set S, any function that you could possibly define on it will necessarily reach some maximum value. This is an example of something called a local to global principle. In this case, we know that each particular value of f is bounded in a way that depends on x, and it leads to the global conclusion that f is bounded by some number over the whole domain. However, if the set S is infinite, this statement is no longer true. There are many functions that will not be bounded. If we consider a set that is compact though, it will still have a very similar local to global principle, even though it is infinite. We can see this concretely by again considering the interval from 0 to 1, including the endpoints. This set has an infinite number of points, so the above statement is false. However, it is compact. And interestingly, if we now modify the statement to be only about continuous functions, it becomes true for the closed unit interval. In fact, it is true for all sets that are compact, and false for any that are not compact. So it would not be true for the open unit interval, nor for the entire real line, which are both not compact. Moreover, by a very powerful theorem known as the Heine-Borel theorem, we know that this statement must be true for any subset of the real line that is both closed and bounded. In fact, all closed and bounded subsets are compact, and vice versa, for a Euclidean space of any finite dimension. There's another related theorem called the Bolzano-Weierstrass theorem, which says that all closed and bounded subsets of Rn are also something called sequentially compact, which means that for any infinite sequence of points in a closed and bounded subset S, there always exists some subsequence that converges to a point in S. So we have yet another notion of compactness. This one was also due to the work of Maurice Fréchet, who said that he specifically came up with it out of a desire to generalize the extreme value theorem of calculus to abstract topological spaces. Though Fréchet was not able to discover the right definition of compactness in topological spaces, his original desire was eventually fulfilled when the extreme value theorem was proved in this more general setting. If you'd like to see a proof of this, I made a PDF that you can download for free on my Patreon. I've also included some more technical explanations related to this video. From this perspective, the extreme value theorem of calculus is just a specific instance of this topological theorem, when x is a closed bounded interval and y is the real line. Though the most general definition for a compact topological space is the one in terms of open covers and finite subcovers, all four of these are entirely equivalent not just for Rn, but for any metric space. It's also in the context of metric spaces, where the notion of discreteness plus compactness are truly the same as finiteness. The analogy breaks down a bit in some general topological spaces, but any finite metric space must necessarily be discrete plus compact, and vice versa. Compactness is an incredibly powerful property of spaces, and once you have one compact space, you can find many more. For example, the image of any continuous map of a compact space will be compact. And the product of two compact spaces will be compact as well. Which is why an object like the torus is compact. In fact, one of the most profound theorems in all of topology says that any arbitrary product, finite or infinite, of compact spaces remains compact. As you can see, these results allow us to find many interesting compact spaces. However, there remain useful spaces in math that are not compact, like the real line. But there are ways to modify it so that it will become compact. For instance, we can add 2 points, plus infinity and minus infinity, to form the extended real line. By defining what it means to converge to these points, the extended real line is compact. The technical description of this process is called compactification, and certain non-compact spaces can be compactified in various ways. Another way to compactify the real line is to begin with the following map. The result is a circle with a single point removed. If we add this missing point, which represents infinity, the space again becomes compact. Similarly, the real number 2D plane is topologically equivalent to a sphere with 1 point missing. Again, adding the point that represents infinity results in a compact space. As cool as all this is, it really is just the tip of the iceberg for the subject of compactification and compactness in general. I hope this has piqued your interest and perhaps motivated you to go off and learn more for yourself. If you want to learn more about Planet Wild, go check out their YouTube channel. You can also see their Yellowstone to Yukon mission in action by clicking right here.